Hello, everybody. So today we're going to be looking at different kinds of sorting. Our first type of sorting that we're looking at is our iterative sorting. Tomorrow, or hopefully the end of tonight, we're going to look at recursive sorting. So the first thing we're going to do is, because I'm a visual learner, is look at this terrible not sorted thing, and we're going to watch a selection sort. So a selection sort goes through and compares it. It's really, really slow. It goes through, it finds the lowest thing, and it's going to bop that to the front. Then it's going to find the next lowest thing. It's going to go all the way through this list. And map.
Get there.
And it's so we can see how this is maybe not necessarily the fastest. I think yesterday we were talking about with Fatima about how nested for loops are generally not the quickest thing to sort something. And this is a really good visualization of why, right? You have our two arrays or other things that are kind of like arrays, or rather we have one array that we're going through twice. So we have this array that goes from position 0, shall we say, to position 86. And each time we have an I here, we have a nested for loop, and we have a J here, this only moves one space for every single time that this does the entire sort. Does that make sense, Henry? Have you ever used a for I in range 0 to 1,000, for J in range 1 to 1,000, 1 to 999?
Yeah, but not like exactly that, but something like that.
Along those lines. So this is our comparison sort. This is our selection sort. We have a little selection, we're comparing it, and it takes forever. In fact, it's taking so long, I can't think of more filler text. So I'm going to stop my share. And Henry, it's your turn.
I don't have the thing, unless it's the thing that's like you worked on last week.
No, this is a new one today. We're doing iterative sorting.
Okay, well, I don't have it.
Okay. So, in the great tradition of everything going perfectly, we are going to look at my code, which
yours is already filled out.
Yeah, it's already filled out. Henry's going to take excellent notes. And we're just going to explain how this works. Henry, are you taking excellent notes?
I'm getting my sticky notes. Hold on. Where's the S? Okay.
And actually, because I've already written this code, I would like for Henry to explain exactly what's going on here.
Okay. We're first looping through whatever elements is in between 0 to the length of the array minus 1, which is take.
So in this case, what does I stand for?
The index.
Good. Okay.
And we're having the current index equal to I.
Which is our
index.
Yeah, our index, and our first instantiation is the number.
Whatever.
What's the first index of an array?
0.
Right. So our current index, I equals 0. And then our smallest index
is going to be equal to the current index,
which
which
is
is 0.
awesome.
And then we're going to do another loop in order to go through the array to find the next smallest number for j, which is the other index,
Which is also an index. Yep.
and the range of the current index, which is currently 0, to and the length of the current array. So if the index in the array is less than the smallest index, which is equal to the current index, then it will return the next smallest index, and it'll update j.
There's a strange sound coming from. Okay. No, Python, stop. There we go. Ha. Python wanted to talk to me.
I just dropped the link for the repo if you want to get it.
Yes. Oh, yes. Anybody who wants to copy that repo, please do. So, yes, that is exactly how it works, Henry. Where is my annotator? So we have our array, our single array, which our initial index or current index is at I is 0. And our last index, let's say 87, because I like 87 as much as I like 86. So I is going from 0, so the first for loop goes from 0 to 86. Our second for loop goes from what number to what number?
From 0 to
now that I'm looking at this, I should have done current index plus 1. Should go from 1 to 87. Always finding ways to optimize. So this is really, really cool. This is a cool bit of Python. Doc, can you explain how this is really cool?
Yeah, so you can, you're probably not used to being able to set two variables on one side of the equal sign and have multiple variables, multiple values assigned to them from the other side, but that's exactly what's happening here. So you've got the first variable, comma, the second variable. On the other side of the assignment operator, you've got the value of the first variable, and then a comma, and the second value, the value of the second variable. So yeah, you can do multiple variables this way. You can do more than 2. You can do as many as you need before you run out of memory. I'm just kidding.
That would be
Anyway, yeah, this is something that's different about Python from JavaScript or other languages too.
So Henry, does this make sense to you how we got there and how it works?
yes.
All right. Cool. We're just going to move on then. This is the simple one. You will have, this is in so many code signal problems. This particular one is almost always an option. It's not the best option, but it is almost always an option, and we always start thinking of the nested for loop for some reason. All right, so
it's called brute force.
Yes.
That you can nest like 2 or 3 or 4 for loops just to get a solution by brute force, and then go back and refactor and clean it up.
That's the step 1. Make it work.
Yep.
All right, so now we're going to talk about the bubble sort. I will change my share back to our, oh no, where did it go? All right, back to our visual sorter. Let's see if it finished. It's still going. Can I make this faster? There we go. All right, that's super fast. So this was our very nasty selection sort. Now we're going to talk about the bubble sort. We'll slow it down so we can see how it works. There, we create a bubble. Now you see here how we're comparing 2 at a time. We're comparing 2 at a time, and we're switching. So it's very slowly kind of normalizing. So if we had a really bad, if we had another array, and we had like 1, 7, 5, 2, 8, 3. We would compare 1 and 7. 1 and 7 are in the right places. And then we move the bubble.
You want to become a data scientist? If yes,
Oh,
then
no, I don't. Who's asking me about data science? Then we switch 7 and so we compare 7 and 5. We switch 5 and 7. Then we move over again and we compare 7 and 2. We switch 7 and 2. Then we compare 8. 8 is a good spot. 3. Then we switch 3 and 8. And then we go through again. 1, 5, 5, 2. 2 goes over here. 5 goes over here. 5 and 7. 5's in a good spot. 7 and 3. 3's in a bad spot. 7 needs to go back over here. 7 and 8. Those 2 are fine. 1, 2, 5. 5 switches with 3 when we compare 5 and 3. Does this make sense? And there we go. That is a bubble sorted array. So what we have made, and this is also something that you'll see in the code signal test, is we make kind of this little like bubble, and we shift it through the array and we compare it to itself. And then we change things and how they go, and eventually we end up with a really cool, nice and organized array. Maybe not the coolest thing. We can pretend that.
I think you call it sorted.
Yes, sorted. Nice, cool, sorted array. We'll do this super fast. I can't even follow what the red lines are doing. Did they finish? No. Yes? Maybe. So we get to the end, and eventually. So now let's go over, and Henry, have you forked the repo yet?
Yep.
All right. Then Henry, you get to open the repo and share your screen. Oh goodness, and I come back in and I got more people. What's up, people?
So,
Hi, Ava.
Hi, Jaja. Hi, Joshua. All right, so we got that selection sort done. Awesome. Now we're going to do a bubble sort. So remember that we have to make a little bubble that's going to go and compare for the entirety of our array. So what is perhaps the first thing that we should do?
Make an empty list.
We already have an empty list. This is going to be in place. So just like this last one, we returned the same array that we started with. It was just sorted. So we're going to do the whole thing in place. That sounds like fun? Ah, look at that. It's super fun. So we're going to start with everyone's favorite for loop. Should we go to the entire array? What did we do with the first one?
You went through, you started from 0 and you went through the length of the array minus 1.
Yes. -1. All right. So that's our first for loop. So we're going to start at 0 and go to the almost end of the array. We're just going to go to 85 instead. So what about the next thing we should do? So that's one loop.
Have a like current and
That was the selection. We're going to compare, and all we're going to do with this bubble that we're going to create is we're just going to compare one part of the bubble to the second part of the bubble, and then those two are going to switch. If they meet certain requirements. So we need a second for loop. For j, in range
Nope, you want to start at 1.
Now, I have... Doc, I can't remember how we got to this one. For j in range 1, length of array minus I minus 1. In range 1, length of array.
I minus 1.
I think that's to shrink the array so that once it's been sorted, we don't like continue over it.
Yeah, so one of the drags about bubble sort is that once it is completely sorted, you have to do one more pass to make sure that there are no more switches. So, let's see, 1.
I've got j minus 1, not I.
For I in range, for j in range. So I have minus I minus 1.
So that sounds weird because I is going to be the first element. You need 2 elements to compare, right? So you need to pick up the first element and the second element for the comparison.
It's because it goes, I think it goes ticka ticka ticka, punk, ticka ticka ticka, punk.
Oh, you're talking a different line. Never mind. Sorry.
I don't know what ticka 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 means.
It goes forward, 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 forward. Okay, cool. I don't know. I really don't know why we have that.
I don't either because, so here is.
Well, because I is going to be the length of the array.
I is the index of the first for loop.
Yeah. So so you pick up your first value. So humor me here. I'm going to do a little thing.
Oh,
I have really protruding commas here. My commas are terribly disformed. I apologize for that.
It always happens to me too.
I'm not going to do this whole array, by the way. I'm just probably going to do the first pass just to illustrate the point.
Yeah,
Okay.
I don't know why I have -I-1, but I agree that it shouldn't be there, but I'm wondering why we put it there in the first place.
So you pick up these first two values, right? What's that for?
They switch places.
Yeah, don't do that.
Don't switch their places. They switch their places.
Yeah, that's gonna mess up my illustration.
All right.
So then you go to wait, not eyes.
I see why it does it. I see why it does it, Doc.
Okay.
Because it's going to the end of the array, right? So the 9 goes all the way to the end.
So that's why it's called bubble sort, is because the largest value bubbles to the end, and then the next largest value bubbles to the end.
That's why we have array -I-1, because we don't have to go all the way to the end each time.
Oh, you're so right. That's exactly right.
There we go. So the length of the array minus I minus 1. No, the minus I is also on the outside of that little array. So delete that. Length of the array minus I minus 1. All right, so.
Excuse me, is this anybody can join this Zoom, right?
Yes.
Yeah.
And which one are you working on? Are you working on?
We're working on iterative sorting.
But is that correlate with any of the projects, from Canvas?
None of the projects in Canvas. This is the old training kit.
Okay.
We can Joanne just shared the repo for today. So if you want to go ahead and fork that.
Oh yeah, I did.
Go ahead and open that up. We're almost finished talking about the bubble sort. So we have for I and for J, and we figured out why we did that. So now we have our comparator.
Right.
If all right, Joanne. So if now we have to if I is our index, so J is also an index. So how do we select? So if array at the index of I, very good, is greater than or less than. So I have.
If it's less.
There we go. If array at index J is greater than the array at index J plus 1. J plus 1's inside. So J plus 1, we're increasing that. So this makes our bubble, remember? So we got this little bubble. Boop, boop, boop. So this should start at 0 because we're using array and array 0 at line 25, range 0. There you go. So we're making a sub bubble, right? So we've got our array. And this is our bubble. So this is J, and this is J plus 1 next to it, right?
Right.
So then we're just going to do that cool little destructuring thing that we did before. So where we have our array at current array smallest, So all we're going to do is array at j, comma, outside, there you go, outside, array j plus 1. So what do we set that equal to? If we're going to switch it?
To the array j plus 1. Or not, yeah. And then
And
the array, the new
Right.
array.
so they would switch places and then shift. And that goes all the way to the end. Let's go back to my screen and take a look at that visualization. And oh, it actually managed to finish. So we'll take another quick look at that at relatively high speed. So we can see how we're moving j and j plus 1 all the way to the end. And then we slow it down. Not that slow. We slow it down. We can see that it goes to the second to the end, and then it goes all the way back to the front. Third to the end. See, that was our I minus 1. Does that make sense to everyone? Does anyone have questions? Does anyone have answers?
How long is this Zoom go to? I mean, I see it says 5 minutes left or change, but
We'll drop another Zoom link after this. We usually do about an hour and a half.
oh, okay. Thank you.
No problem. Does anyone have any questions about the selection sort or the bubble sort? These are really good ones to go ahead.
Sorry.
Data?
Theta, yeah, like theta fajita. What was it? So the bubble sort, yeah, the highest values bubble towards the right, but then the selection sort, what's the summary of that?
So the selection sort, let me just go ahead and, it doesn't seem like I can restart that, so I'll just refresh it. The selection sort is the standard brute force.
Oh, it compares one next to with the next one over, and then you push, and then
where it's a nested for loop of just like our previous.
It identifies the smallest element in the array. That's the first step, right?
Yes. So our selection sort, we identify, we have our current index set at 0 at our index. Our smallest index is equal to our current index. We have a nested for loop here where we're comparing, move pen, there we go, where we're comparing, so this is our I, and then we have the massive list that goes to 8. And our j moves 1, 2, 3, 4, 5, 6, 7, 8. Then our I moves up 1. And our j moves all the way to the end. If our array at j is smaller than our array at our current smallest index, then we're going to finally, at the very after the entire for loop executes of array j, then we will switch our current index with the smallest index and the smallest index with the current index. It is the easiest sort to learn, but is the slowest sort time-wise. The bubble sort is slightly faster. Does that make sense to you, Tita?
So the current one is just the one that you have, like that you're looking for in the array, and then
is our current location. We're not looking for anything. This is just a sort. We're just putting things in order.
Okay. Yeah, so it's where you are currently, and then it always iteratively compares to the next. It doesn't compare to the next element, or it does?
So in our little array that we have here, so we have I, and our I stays static while j compares to everything in the array. And then after J has gone through J, 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 all the way to the end.
Oh, I see. Then it compares I and J.
Yes, then it compares
Like that.
while it's comparing. So it compares this, and wherever our smallest index is, let's say that we have a 1, our number 1 somewhere up in here,
Yeah.
then we'll take the index of 1, and that will be our new smallest index. And then J will continue on, J, 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 J. And then it's going to move 1 to the front, and then I is going to shift over. So then I is going to go here, and then J is going to go all the way back through that array until we find the next smallest number, which let's say is 3. And
Okay.
then it continues like that.
All right. So yeah, to do it, you need the nested loop and the 2 indices. Thank you.
No problem. All right. Since sorts are kind of fun and easy. Oh, the counting sort. Who wants to do the counting sort? We'll do it after our break. Welcome back. Okay, so now we're going to talk about the counting sort. This one is kind of hard to explain with words. So I'm going to go ahead and look at our visualizer, which I found. And we're going to look at our counting sort. So essentially what this does, where's Doc? Joshua, what does this do?
This counting sort. Let's see. I wasn't even looking at the screen just now.
This is one of the more complicated, but also really quick sorts.
Yes.
But I do not remember how it works. I can write it, but I don't know what it does.
So,
It eventually gets everything in order. Let's take another look at it. Is it going? Pause, play. Slow down.
speed's too high.
Counting sort. I think this is where we spent a lot of our time the first time we went through this. Okay. From the TK, the counting sort is a sorting algorithm that works on a set of data where we specifically know the maximum value that can exist in that set of data. That's our important key phrase, where we already know the maximum value. The idea behind the algorithm is that we can create buckets from 0 up to the maximum value. This is most easily done by initializing an array of zeros, whose length is the max value plus 1. Each of the buckets, then, is responsible for keeping track of how many times we've seen I in the input set of data as we iterate through it. Once we know how many times each piece of data in the input set has shown up, we can construct a sorted set of the input data from the buckets. Does that make sense to everyone? Does that make sense to anyone?
No.
Yeah, let's think about that again. Buckets are just like groups of them, I guess, and you already know the highest one, and then what you're comparing the highest one with the highest one of each of those buckets or groups or something like that.
So let's start by looking in our by looking at my code.
Yeah, there's a lot of online Google Quick videos too that are good. And when I took some other classes, I'd have to remember what, but in color coding is cool.
So we first instantiate our 2 buckets with out and count. Can anyone remember what this specific bit of, oh gosh,
It's
My
the
word.
same.
What is this called?
It's the list.
List compilation. List
Comprehension?
List
comprehension.
comprehension. Very good.
What's the
So-
difference between that and a list? I forget. One's like mutable.
A list comprehension is basically a JavaScript for each.
Oh, it's for JavaScript. Okay.
So a list comprehension is you have, what are you going to do? So your X for, so you have your variable or your or whatever it is you're going to do. You could do X plus 1 for X in list, but you have whatever this is. In this case, we have 0 for I in range length of the array. So this basically creates a massive bucket, shall we say, of zeros until the end of the array that we have. 0, 0, 0, 0, 0, 0, 0, 0, 0. This is kind of similar. My catchphrase. This is kind of like something that we do in hash tables later, where we create a representation using hashtags. So first thing we're going to do is we're going to create a representation of the list with zeros. So let's say we have a really short list. Let's go with 6. 6 zeros. Then we have a count. So can someone explain to me this list comprehension? Anyone? Bueller? All right.
So for I in range maximum,
So
you'll just make an array full of zeros,
how many zeros?
however many maximum is.
What's our maximum? Let's pretend we have a maximum.
See, maximum. So right now, maximum is none. So if you had like 1, then it will be 1, 0 in that list.
So our default maximum, if no one gives us a maximum, let's give it a maximum. I gave it a range. Our array is going to be 6 long, and our maximum number is what?
12.
12. All right. Yay. So how many zeros do we have?
Well,
12.
All right.
but why would we want all that? ...
12 zeros. For this particular algorithm, that is why we want it. I am really bad at this one. I don't.
This is like the divide and conquer algorithm.
Yep.
Like, I sent a link, but like just to visualize it, it's pretty good. It's a pretty good visualizer.
So we have our array passed in. So the first thing we have for I in array, so for each number in our array, count of the number plus equals 1. There's probably a better visualization than the one I have. So we increase our count in our counter at the index of the specific index by 1.
So it will make an array of the numbers 1 through 12.
It will increase. So it will basically say, hey, we have this number. So we have an array that is only like 6 things long and our maximum number is 12. Is that going to have every single number between 1 and 12?
Oh, no, of course not. Right.
There we go. So it says, okay, well, these are numbers we have in these specific locations.
Right. Okay.
Wait, what was that?
These are the numbers we have in these locations. So drawing it out again.
I got a question.
I do not have answers.
Well, I hope you do.
I'll try.
So using I repeatedly for the 3 different for loops, that's not going to mess it up.
Nope, it will not, because they're not nested.
Okay.
If they were nested, it would mess it up.
Okay.
So we're going to go with 3 and 4 in this instance because that's smaller. Okay, so, and then we have our actual array, which is 4, 3, 1, just to give us something to do. So for I in array, count I plus 1, plus equals 1. So here's our array, 4. Here's our count. Count array. Let's go back to the visualizer. Skip back, counting array. So 25, here's our bucket. Here's our 2 buckets, our bucket and our array, right? So this was our first bucket, which is our maximum value, right? Can we get like some faces in here other than Henry's? It's easier for me to see if I.
I'm chasing babies right now. Sorry.
It's okay. It just makes me feel really uncomfortable to
Oh,
see nothing but black screens.
I was just thinking, this is the one, the website that I had gone through before when I did data structures. But anyway, so
All
yeah,
right.
maximum index.
So this is our maximum value, and this is the length of the array. So you see how we have essentially buckets of nothing. These are our zeros. These empty boxes would be the arrays that we instantiated, right?
So this is the only sort where we do have to, fill them with zeros, though?
Yes. Probably no, but the only one in this particular homework.
Oh, I see.
So we have. So now we'll take a nice slow go. So 25, here's our arrays. We're comparing, we're adding at our index plus minus things. 16. Now,
I'm not sure what
there's
it's
2
doing.
8s. There's an 11 at 10, 26 at 11, a 12 at 12, 27 at 13 plus 1, 14, 15, 16, 17, 18. I'm not really sure what's going on, to be completely honest, and I'm lost and tired.
I'm
And
lost too.
I don't remember who explained this last time either.
I mean, we're just Googling it. It says counting sort, is a stable sorting technique used to sort objects according to the keys that are small numbers. So I guess the keys are the indices. It counts the number of keys whose key values are the same. I'm not sure, but this sorting technique is effective when the difference between different keys are not so big. Otherwise, it can increase the space complexity.
All right, here we go. For I in the maximum range, count I plus equals count of I minus 1. And then our final, for I in range length of array, output bracket count bracket array at I, 2 closed brackets minus 1 closed bracket equals array at I. Count array at I minus equals 1, and our array is equal to our output, and we switch everything. Your time, it makes your time complexity better, but your space complexity is a little bit harder because you've made so many separate things. And I really do not remember how we solved this, or if we just copied it. So we go back through and we're comparing and we're comparing. And we can compare these locations. And it goes backwards. I really think Harry must have been in here this night. All right. Now that everyone is confused, Joshua, are you sure you can't explain this one?
I could give it a shot.
You're gonna do better than me. You can definitely do better than me right now.
All right. So in my code, like I wrote out it. What I'm doing is like,
Share your code.
all right. So yeah, I'm using counter here, and basically if the maximum value is none, I just set it to 0. That way it doesn't error when it gets to this part. So yeah, set max to 0 if it's none, and then I have a dictionary because counter returns a dictionary containing like the keys being the value of an element in the array, and the value being the number of elements of that element in that array. You know what I mean? And then I have an array here that I created, and yeah. So for I in range 0 to maximum +1. Why did I do this? Yeah, so it'll be inclusive. So maximum will be inclusive. See, I'm passing in 4 as the maximum here. But if I just have it like this, it'll just go up to 3 and then stop. And then I have a conditional statement here. If I is in the array, which I probably could have, looking back on it, I probably could have did a lot better with it.
Okay, I see.
I'll just append.
So you had a larger array going in and a smaller maximum at this size, which was 4, and your array was like 50 long. So you would have had an instantiated bucket with 50 zeros, etc.
Yeah, I guess I can run this real quick.
And then a smaller bucket with 5 zeros, because 0 equals 0. Because the first one is 0 and the final one is 4. 0, 1, 2, 3, 4.
Yeah, so that's what it does here. Like, just
Then it counts how many of each number are at each individual place, and then it switches it up accordingly. It's nice that you've got that printout. It's easier to see.
Maximum would be like the biggest number in that array. Yes, I'm not sure, but
it's the largest number in the given array.
Yeah, so it's like 4. But yeah, and then I have list comprehension. This is the one part where I said that probably could have did better because it's nested like this, 2 for loops. I was lazy, and it works. But yeah.
So does everyone get that visualization a little bit better? This one has not popped up in any of the GCA things, but it is nice to know how to write it.
Yeah.
I just want to get the concept of it. It has to do with hash tables, which seems fuzzy for me.
Yeah, hash tables, that's just like key value pairs, right? Like let me print this out.
There is, I think it's in the hash table one where it has a visual representation of a numeric value. So it would just be like, when you're installing something on hey, what's that thing called where it's just a bunch of hashtags? It's in a hash table and it's a visual representation of numbers. What are those things called? Hash maps?
Oh,
Yeah.
that sounds right.
That's what it's called. Hash map.
It's
hash table, something like that.
It's like a hash map, and whenever you see it every time you download something in NPM, and these little things go all across your screen.
NPM, I don't know what that is.
Whenever you install or whenever you update Conda, and you see these little hashtags go across your screen from 0 to 100% to show your progress.
We've been using VS Code, so I'm not quite sure.
You npm install stuff down here, and it like gives you a visual representation of how far along you are in your install.
Okay.
So that's kind of that's what a bucket is. Is it just a visual representation of something, or in this case, a slot in memory that represents something that you haven't finished yet?
Okay.
And then it fills up as it completes,
Okay, that's cool.
just like a bucket.
So okay, just a real basic concept, higher level. So counting sort, yeah, you have to know the maximum value in a given array, and then you're trying to sort that, or you're trying to sort that array, or what are you trying to do? Like,
Yeah, you're trying to sort the array that's passed in, right? Like
A histogram. That was the word I was looking for, Josh. Histogram.
well, yeah, it sorts this away, right? Like, and
you already know the maximum, it just sorts the other values, right?
yeah, well, yeah.
Okay.
Actually, well, it sorts all of them, right? Like, because let's say I say for I in range like 0 to maximum, right? Like, and let's say I add 99 to this, right? Like, that means theoretically this is going to happen 99 times, right? But it won't append those middle numbers, like from 4 to 99, 4 to 98. It won't append that to my array, right? Like, it'll see that and see if this is true, Like,
So you have 0, 1, 2, and 3 in your previous, and you have this massive array, and this counts how many times these numbers appear. And then each time one of these the number 1 appears, and it puts a little 1 each time it sees a 1, and it puts a 1 each time it sees a 2, and a 1 each time it sees a 3.
Oh, okay. So yeah, it just keeps track of it.
And then after that is complete, then we disregard. Then we kind of disregard it, but we keep it there. And then each time there was a 1, we go 1 minus 1, 1 minus 1, 1. Okay, there were 3 1s, 2 2s, 2 minus 2, 2 minus 2, and 1 3. No 4s, no 5, no 6, no 7, no 8, no 9, and 199. In that way. Does that make sense?
I mean, basically you have an array, you know the maximum, and then the algorithm makes a bucket, which is almost like, I guess, a hash map, or it's almost like another array, right? Like where it's...
Yes, we're making an array of zeros.
So you have to initialize an array of zeros, and then you gradually change those zeros to be the count of the numbers of the elements that it comes across in the array that you're sorting, right?
Mm-hmm.
That's the simplest definition, like kind of description.
Yes, that is the simplest description.
Thank you.
There we go. You got us there. Thank you.
Mine just doesn't use the zeros.
Like, I don't remember this from like either Java or C++ data structures.
It is a stretch problem.
Maybe it was under like the hashing. So I don't remember. That was years.
This was a stretch problem, so we just went over it because we're cool like that.
Like, this is all just
this is volunteer. This is not with Lambda. We're not associated with Lambda other than that we are students. Baird disclaimer, we are all volunteers.
Nice.
Just like helping each other out. Let's hit those searching algorithms.
That's where I was at with the, the binary tree search and all that. I mean,
I go ahead and hand over.
Hey,
before you do this though, can I see your bubble sort algorithm real quick?
Yeah.
Bubble. Let's see.
Wait, nice.
So do you guys meet every night at 5? Or whatever, at 8?
Yeah, we meet every night.
Oh, okay. Yeah. Good to know.
Does this work?
Yes. Are you talking about this part here?
Not just line 24.
Yeah.
I was thinking, I don't know. Like I tried, I'm trying to implement it in my code.
Try this one. I think I might have had the -1 in the wrong spot. Yeah. That should work.
So just take the -1 out.
Yep.
Let me see real quick.
That should do it.
Because I have to see what else. I mean, we have those track team things. So I don't know if I have to meet with my group, but like if it's cool, I might hop in and out, and then also, but or just like not say anything, and then, I don't know.
It's all good.
Fine.
Yep.
What I was saying, let me share my screen real quick.
All right.
Just so I can.
Go ahead.
Try and
We got 10 minutes. You can share yours.
this out because this is my original code, right? This is yours.
Right. So Alt. Okay.
I'll just take this out, right? That's what you said, right?
Mm-hmm. That should have done it. Because I think that's what we did in Henry's before Henry ran away.
I get an index out of range on 29. Yeah, I get an index out of range here.
That's why it has to be. Oh, it's Josh. It should be -I -1.
-I -1.
Yeah. So for I in range or length array, and then -1, because the +1 is what throws it.
Let me see. Let me see this.
That should do it.
3, 4, 5, 6, 7, 8, 9. That works.
There you go.
Is this already sorted out?
Yeah.
Let's switch this around.
Just curious if you guys will be available also doing this during the 2 weeks coming up that we have off for the holidays.
What?
Yeah, Bearden doesn't take a break.
Yep.
Okay, no, because I'm super behind, and then like that would be a good maybe opportunity to catch up.
Yeah, man. We don't ever stop.
Nope.
That's not good enough.
So that looks like right here. I'm getting out of range. Maybe that's why you had -1. Let me see.
That's where we had the -1 up there.
See, so I get that.
It says that your comparator's not supported between instances of list and integer.
List and integer.
Yeah.
List. Make an index j. List. Index j +1. What? Oh.
There you go. Okay.
Let's see.
There you go.
There we go. There we go.
It's not my code, man. You are just sleepy.
Yeah, that's all.
All right. Alrighty, now let's talk about some of these searches. Searches are pretty straightforward, so we're not going to have to do too much to do. We've got two types of searches, the linear search and the binary search. There's other types of searches. These are the two we're talking about. So before we talked about when we were putting our binary search trees together in the previous week, we talked about how binary search was way, way, way faster. Anybody can remember why?
Because you cut it in half, then you cut it in half, then you cut it in half, and keep going.
Yep.
Because a linear search starts at 0, and it goes and it checks every single thing in your array / list / whatever until it gets to your target item, which is X in this case. A binary search, on the other hand, checks if it's in the middle. If it's not in the middle, then we do a comparator, and then we cut it in half and we go to whatever side it is. And then we check in the middle of that, and then we go to whatever side it is, and we check in the middle of that, and on and on and on and on and on until we get to the X. Sometimes it's more efficient, sometimes it's less efficient, but overall it is more efficient. So, linear search, a lovely bit of Python, my personal favorite. Josh, are you still around?
I am here.
All right, explain me. How does this work?
Okay, so you have if the target in the array. So you're going to have your array and your target as your parameters. And you're stating that if the target number or whatever you're searching for is inside of the array, you want to return the index of that target.
Yes.
Otherwise, it's not there.
Exactly, which is a really nice built-in linear search. Otherwise, return -1 as false. All right.
What was that other thing you said besides that binary search is much faster, because we keep cutting up the array or whatever in half? Is just that it's iterative and it compares what you're looking for with every single like progressive element?
No. So a linear search looks in every single drawer.
Yeah.
And every single index. Every single one until you get to your target. So if we have a sorted array that goes from 0 to 999, because I'm be complicated.
Yeah, it still has to go long.
It's going to go all the way to the end before it finds 9,999. So the number of steps that this is going to take is 1,000 steps before it gets to the end. Honey, can I have the plug, please?
Wait, how is that different from what I said? I said the target you're looking for has to.
The binary array cuts it in half and checks left and right.
Yeah,
it cuts it in half, checks left and right.
Yeah, no,
and then if it compares greater than or less than, so it takes less plug. It takes, sorry, it takes less time because it's making less steps. And it's got a comparator in there, and that is why that one is more useful. I think I might have misinterpreted what you said.
Isn't that log n or n log n or something like that?
Yes, something like that. I'm not good at the time complexities.
Yeah, there's that pretty
Yeah,
chart.
it's in log n.
In log n.
But log is always base 2 if it doesn't otherwise state it, right?
Anyone good with numbers can answer that one?
What was that?
Log is it's always base 2 if it doesn't say otherwise, like in math or computer science.
Well, yeah, it's base 2 in computer science normally, I think, because it's binary. I think that's what Beach told me. I trust them.
Defined like that. 2 to x equals like log 1 or whatever the heck is like in math.
Log 2, yeah, that's what Beach told me.
So nobody has the where you can make. Maybe I can see if mine has no time limit, but I still have to check about it.
These don't have a time limit because these are.
Oh, it just says
code signal.
Oh no.
These are Python. If this was a code signal, there would be a time limit. With our binary search, this is just the iterative example of a binary search. Last time we talked about how to use recursion to make our binary searches a little bit smaller when it comes to this little tree here. Remembering that recursion is a little bit more expensive time-wise than a while loop. So this is an iterative implementation of a binary search. We instantiate our left because our left node or our left is always the smallest or the largest number.
Left is always the smallest.
Right. So we're just going to assume that it's 0. It's a bad assumption, but whatever. And we're going to assume that our right is going to be the butt of the array. Now, here we go with some math. So as long as left is less than right, we have the middle. And the way that we get our middle is by adding left and right and dividing it by 2. What's special about this double divide here?
Storing.
Does it, what, yeah, it does a,
Yeah.
Returns an integer.
that's right, it returns an integer, not a float. So it's going to give us a whole number, so we have a middle. And this is the important part. All right, so Tita, go ahead and read this code block for me.
All right, let's see. It says while left is less than right, middle equals quantity left plus right, floor divide 2 by 2. If array at the left position or whatever index
At the index of the left.
at the index of the left equals target, then return left. If the array at the index of right is equal to,
So does this continue the code, or does it stop it?
well, okay, let's see. So we're saying if array at left, right now it's set at 0. If 0 equals target, what's our target?
Well, if the array at index 0 equals the target.
Oh, okay. Well, but I don't know where a target is.
So if this happens, if the array at index of the left is equal to the target, stop the function, return the left.
Well, but I don't know what target is, but
Target's been passed in here.
oh, okay. It's just whatever. We don't need an actual value for that.
The target will be passed a value, so we would have an array of like 0 to 550,
Yeah.
and our target would be 17.
Okay. So in that case, I mean, it's just saying, I think it's going to return left. It's well, we don't know because we don't know the target yet.
Yeah, we do know the target. It's been passed in, and that's what we're checking to find. This is what we're searching for.
Oh, okay. So that it'll return that.
So if
0.
So is array at 0 17? Probably not. So that's what we're checking.
Okay.
So
So then it'll go to the next line.
At 0 the target, yes or no? No.
No.
Then we check
if the right node,
if the end of our array.
Okay.
So array at -1, for example.
Well, what? Oh, okay. That's just an example. Okay.
Yeah. So array at the very end. Is that our target?
No, it's not 17.
Then what do we do?
We're gonna return the -1.
So that we're not returning anything, we're going to the next one.
Oh, because it's not equal. You're right. Just kidding. Okay, so yeah, if the array at the middle index equals 17, return middle. I mean, but
is it 17? Let's say it's not. It's probably not. Between 0 and 550, probably not 17.
I just don't know how to do it without like literal actual numbers, you know.
So we're guessing. We're just kind of guessing. So if it's on the left and it is the target, we can stop the function and return the left. Otherwise, we have to continue the array and we look to the right. Is it the target? If it is, we stop the function and return our right index. Otherwise, we continue on and we look in the middle. If it's in the middle.
Oh, okay. So I'm thinking like a search tree. This is not a tree. This is just an array.
Yes, this is an array. It could be a search tree. You could think of it as it's the same concept as a binary search, as a binary tree, and doing a search on the tree. We start here, look left, look right, cool, greater than, less than, move. Left, right, greater than, less than, cool, move.
But then what would be the middle thing? The middle, because I'm trying to think like.
Middle, the node.
It would be the actual node. Okay.
Yeah, node is middle.
Like the current node.
Current,
okay.
Yep.
Thanks.
All right, middle. Cool.
So yeah, so if the current node or the array at that middle position is greater than the target, whatever it may be, you're gonna assign it to the right.
So now that is the dividing in half of the array.
Oh, maybe we could put a comment there. Whose code is this? Oh,
this is fine. This is my code.
Oh, I guess you don't need to put copious comments or.
I'm really not a commenter, unfortunately.
No, because you know this stuff. That's cool.
Um,
I'm still illiterate.
so here we're checking if the middle is greater than the target. If it's greater than our target, then we reassign right? So we have a right here. We're going to reassign that as the middle. So we take our middle value, which here was, I don't know, some random number, 46 perhaps, and we're reassigning it our right as that, which, left is still great. Left is still less than the right. So it's going to continue, and we're going to go all the way back to the top, and we're going to do this while loop all over again until we find it. Clear?
Ah, okay, because you always want the larger numbers to the right. Okay, that makes sense. Otherwise, it'll go to the left.
Yep.
Okay.
Everybody got that? It's just a little binary tree. Just a little binary tree. I have 2 extra searches in here because I'm a dummy. But you don't need these 2. But I have them. So if the
Why wouldn't you need them?
Because you technically don't need to check the left and the right, because if you never change it, the left is always going to be index 0. It's always going to be the same each time. It's an extra step. So it adds milliseconds.
Do you end up sharing all your repos from your lessons, the meetings?
I don't share my repo. If you're following me, you can definitely find it.
Oh, you can follow somebody on GitHub?
Yeah, you can follow someone on GitHub. All of my answers are on GitHub.
Yay!
They're not always the best answers. I got lucky because when I was doing this the first time, we had Harry and Doc in the room the whole time, and my code got beaten. Anyone have questions on binary search?
Yeah, so I'm trying to gauge like what kind of questions would be asked whenever using binary search. Like, is there anything in particular that you would look for whenever you're getting coding challenges that will warrant you to use a binary search?
So the binary, if they're like, find this in the array.
Okay.
Binary search.
Okay.
It shaves like, it's basically essentially it's twice as fast.
Mm-hmm.
But I always do a linear search first because there's a chance that it might just pass.
Gotcha. And it's quicker.
It's just faster to type. Binary search is faster.
Yeah, as far as runtime, binary search is faster, but it's quicker to type a linear search.
Yep.
Now, whenever the problem that I typically have that I need to practice with is when you get the coding challenges, sometimes they'll give you like where you only have one parameter. And with the binary search and linear search, you typically use 2 parameters for that. And so how would you implement that if, like, let's say they're asking you, well, I guess they wouldn't, right? If you're searching for anything particular inside of an array, they're going to tell you 2 parameters in that, right?
Yes, unless they're telling you to return like the min or the max. And
in that case, you can just use what Python provides you, which is min and max.
Which actually is a really slow sort.
Ah, okay.
So min and max is great for comparing like 2 numbers, but if you have a massive like 5 million thing list like they like to pass you in the code signals,
yeah, that's
when you would need to use these sorting algorithms.
Okay, and so how would I basically convert that into something? So will I create my own binary search and then return whatever I needed from that and then pass it into the function that they've given me?
So, okay. Why don't we... I really don't want to run extra study sessions because I'm already running 2. But Taja, why don't you come to the Unit 1 thing tomorrow, and if no one else is there, we can talk through some code signal stuff and some strategies.
Perfect. What time is that?
It's the hour before, so it's 7 Eastern.
Okay, so 5 my time. No, 4 my time.
4 your time.
Yeah.
So if you guys have computers like code signal questions,
Mhm.
I cannot guarantee you that I can find the answer, but we can talk through and come up with some strategies for identifying things.
Please, you're a saint for doing this much. So appreciate it.
Anytime, as long as those times are at 4 and 5 p.m.
Gotcha.
Yeah, we're actually really ahead in labs, so I can actually afford to take time. But
No, you have personal time too, so you got to take that into consideration.
so we can talk through some of them. I will not solve them for you. I will help you see kind of where to use some strategies that we're talking through.
Right.
They don't really go through this, but Doc and I were talking about this earlier. Step 1 to solving anything is to make it work.
Mm.
So is it returning the thing? Great. How many tests is it passing? Cool. Step 2 is make it fast. Step 3 is make it pretty. So step 2 is where you start optimizing. So a linear search is step 1, right? If we're doing a search, cool. Does it work? Awesome. Does it pass our time constraint? No. So our next thing is, okay, cool, we know how to do a binary search. Neat. Does it work? Is it fast? Awesome. Oh man, this code looks terrible. Let's clean it up.
Got it.
So a lot of people try and write the most optimized thing first. And they get hung up in something that honestly might not even be what they're trying to do. So get it to work first. It might be ugly. It might be the most time and space intensive thing, but you got it to work. That's step 1. Step 2 is make it fast, and then step 3 is clean it